Hey guys, this is Miss Wiesner. This is the second part of this linear relationships. This is actually one lesson that I'm pulling from, but it just seemed to be too long, and I thought it would be easier if I put it into two separate lessons. And then I realized that when some of you were doing the constant rate of change, you were looking at the tables the way you need to look at them when you're looking to see if they have a proportional relationship, which is what we're doing today. So today you're going to learn how to identify proportional relationships and what makes proportional relationships unique. What's so special about proportional relationships? Believe me, they are a big deal in algebra. So there are two specific standards that deal with proportional relationships. You have to be able to graph them, and you have to be able to compare two different proportional relationships given multiple representations. Just like I told you before, you can see them in tables, in graphs, ordered pairs, equations, diagrams, verbal descriptions, whatever. You're going to have to be able to do all of that stuff that we did with constant rate of change with proportional relationships. So a lot of this lesson is going to use the same problems from the constant rate of change. And there's little Allie Pooh. Now, if we think back to the first problem that we had when we started with constant rate of change, we made a big deal about looking at graphs this way. The change in y over the change in x. So we didn't look at the numbers that were in the table. We looked at how much they were increasing on the outside. Remember? And then that's what we used as a fraction. So what the change was in y, we would put that over the change in x. Well, that's not what we do for proportional relationships. But before we get started, I'm going to tell you what it is. Okay, so a proportional relationship must be linear. So in other words, it has to have a constant rate of change, and it must have a constant ratio. Well, what in the world is that? You don't know? Well, you're getting ready to find out. And this is what some of you were getting confused with, even though you didn't know it. You weren't aware of it. But the constant ratio is what I'm going to show you with that first table. Okay, just like yesterday, or in the video earlier if you're watching it today, when I look for the constant ratio, I have to remember that it's how the y's are changing, so they're going up by 2 each time. At the same time, my y's are changing by 1. Now, you know that there can be some of these data pieces missing. That's why we have to look at every single one. And then I didn't put them as 4 different fractions because I didn't need to. But if you have to, you will, and then you'll reduce them and see if they have the same rate of change or a constant rate of change. So is this a linear relationship? Yes, it is. So that's the first piece. Now, what's this constant ratio business? Constant ratio. What in the world? Well, it's what some of you are probably trying to do without even knowing it, and that's why I had to kind of stop this for a second. That's when you're looking at y and x together. Okay, constant ratio is y over x. Okay, so what are your y's doing when you put them over x? And you have to look at all of them. So this is where you're looking at the actual numbers or number pieces of data. And I could tell by some of your work yesterday you weren't putting that in the fractions. You weren't putting the rate of change in the fractions. You were putting this actual data into fractions. And so you were figuring out, even though you didn't know it, whether or not it was a proportional relationship. It can be linear and not be proportional. Okay, so all of these reduce down to, happen to reduce down to the same thing. So this has a constant ratio of 2, and it has a constant rate of change of 2. So this is proportional. Yay! Now, if I'm telling you something's proportional, you're automatically going to know, hey, it's linear. Now, here's that same relationship put in the graph, okay? And so you would still do it the same way you did before. You can actually look at this graph, and I'm going to tell you a secret, but the way that the graph looks means a lot. And really all that you're worried about when you're wanting to see if it's proportional when you're looking at a graph is, first of all, you got to know the ordered pairs, and we already know what they are because they're in that table. But you see how this goes through the origin. So proportional relationships go through the origin. So if it's proportional, you'll be able to tell by the graph because it goes through point 0, 0. Okay, this is another one that we did the other day, and I noticed that you were putting the wrong numbers in for fractions, and I didn't want you to get confused. But to find out if it's linear, it's not proportional if it's not linear, so we got to figure that out first. That's when you're looking at this, the outside. Okay? And we found that out yesterday, that as the transactions go down by 30 and the number of transactions, so for every third transaction, the balance was decreasing by 30. Well, that's not a good constant rate of change, not in the correct form, so the constant rate of change was negative 10. All right, or negative 10 over 1, whatever. Now, to see if this is proportional, you don't look at the sides. You look this way. Okay? So what I'm going to do is I'm going to take my y's and I'm going to put them over my x's. So this is y and this is x. So I'm going to put 170 over 3, 140 over 6, 110 over 9, and 80 over 12. Now, take a calculator if you've got one handy. Of course, I don't have one handy. 170 divided by 3. I know. All right, so 170 divided by 3, that gives me some wicked number, 56. Well, I know 0.6 repeating. I know that's 2/3. So 56.67. So that's kind of giving me a hint right here. And now I'm going to look at 140 divided by 6. If just one of these is wrong, then the entire thing is not proportional. I can already tell that since these two do not match, this entire thing is not proportional. But just to prove to you, that's 12.22, and 80 over 12, that's 6.67. And maybe I'll show you what that graph looks like in a few minutes. There's Mr. Martin texting me. Ugh. About tech talks. Ugh, we don't like that. Okay. Okay, and I just had to ugly that up. It's linear, but it's not proportional. Okay, so it doesn't have a constant ratio. All right, so that means that it doesn't cross on a graph 0.00. Okay, let's look at this one from yesterday. This is linear. This was one of our equations to see if it was linear. We knew that the x's were going up by 5 minutes, but we knew that the temperature did not start cooling off at a constant rate. So this is not linear. Okay, because I think that the constant rate of change was -5/5, and that didn't equal -4/5. So it could not be linear, and if it's not linear, guess what? It's not proportional. We can go through and divide it all out, and it may look like it's proportional, and it could very well be based on what this says here, but when you graph it, it's not going to be a straight line. So it has to be a straight line. If it's not, then it's not proportional. Okay, so let's look at this graph. We've got remember this one was one where the time was mixed up. I don't think that it's going to be proportional because there's 0.00, and it doesn't look like the dots, whether you put them upside down or whatever, they're not going to cross the origin. But all right, here's another one real quick. First we have to find out if it's linear. So does it have a constant rate of change? And if I remember correctly, this was 6 and this was 5. So yes, it was linear, and the constant rate of change was 6/5, or 6/5. Now let's see if it is proportional. So what we're going to do is I'm going to change my color here, and I'm going to look at these. I'm going to put 6/5. I'll put 10/12, and I'm going to put, I'm sorry, sorry, messed you up there. I'm going to put 12/10, excuse me, and I'm going to put 18/15. Now, as long as these all reduce down to the same thing, then that'll be a constant ratio. So let's see if it has a constant ratio. All right, well, 12/10, so 2 goes into both of those, so 6/5 is the first one. Now, 12/10, so if I divide that by 2, that 12/10 becomes 6/5, so that's good. And then let's divide that by 3, so we're reducing. That becomes 6/5. So the constant ratio is 6/5. So yes, it's linear. And yes, it's proportional. Okay. And the constant ratio is 6/5. You'd have to do some. Okay, this is the airline one, and it is a linear relationship. We did figure that out yesterday, but it's not proportional. And I can tell that because I'm looking at the graph. Not proportional. Because if it's proportional, remember the line should go where? It does not go through the origin. And then we also know that there's no constant ratio. Well, there might be a constant ratio. It can't be proportional if it's not linear. Let's see if it has a constant ratio. Okay, just wanted to show you that we can't divide 3,500 by 0. It's undefined. We'll learn about that later. And so then I just looked at these two. And 3,000 divided by 2 is 1,500 to 1. But when I did the division here, it came out to 1,000/3. So it does not have a constant ratio. Okay, so this was an example, and I don't know what happened to my table, but it's on your PowerPoint or your Google slide. But we're comparing two sets of data, degrees Celsius and degrees Fahrenheit. I'll put my little degrees, my little circle there. And so we wanted to see if if this is an example of a proportional relationship. Now, it can't be proportional unless it is linear. So let's check that out. So that's 5, that's 5, that's 5, and that's 5. And then the Fahrenheit goes up. Remember, we're just going up by 5s here. So when it's 0, Fahrenheit is 32. There's no ifs, ands, or buts about it. Freezing in Celsius is at 0 degrees, but freezing in degrees Fahrenheit is at 32. So water freezes at 32 degrees Fahrenheit, but 0 degrees Celsius. So this is data here that's true beyond all get out. 32 to 41 is 9. 41 to 50 is 9. 50 to 59 is 9. And that's also 9. So if we're looking at the change in y over the change in x, these are all the same. So I'm just going to put 9/5. That is my constant rate of change. So I know that this is linear. Okay, so if I graph these, it's going to make a straight line. That's great. Now I know that it's linear. I have to check to see if it is proportional. So that's y and this is x. I can't do anything about that. I can't say 32 divided by 0. That's undefined. But I can say 41 over 5. I can say 50 over 10. See where I'm getting these numbers from? Straight from the table. 59 over 15 and 68 over 20. Well, I tell you right now, it doesn't look too good. So 41 over 5, that is the same thing as 8.2 or thereabout. 50 divided by 10, that's 5. So I already know that this is not going to work. But just to prove it, this is approximately 3.9. So I don't even need to go any further. I already know that there's not a constant ratio, because the numbers are changed, the fractions. So it can be linear. So yes, it's linear. No to proportional. There is no constant ratio, and here is the math to prove it. Okay, here is your data from Fahrenheit and Celsius. So if I plotted that information on a coordinate plane, you can see that it is linear. So yes, it's linear, but does it go through the origin? So no for proportional. That was just to show you, to prove to you that it doesn't go through the origin. Does not go through .00. Okay, and this was your homework for the proportions, and I said you don't have to worry about it because I'm going to do them for you. Actually, the instructions are all the same, but are the same from the constant rate of change, so I'm wiping it out for you. Now, what we're going to do is, first of all, let's try to remember if these were linear relationships, and if they were, we can go ahead and see if they're proportions. I believe that it was 3. The constant rate of change was 3. Okay, so this was linear. Let's see if it's proportional. So I have 15 over 5, have 24 over 8, 36 over 12, and I got to check all of them, 72 over 24. They all have to be right, but if just one is wrong, then everything else is wrong. Okay, so 15 over 5 is 3, 24 over 8 is 3, 30, that's 3, and that's 3. So the constant ratio is the same thing as the constant rate of change. That happens sometimes. It is 3 to 1. So this is linear, and it's also proportional. I don't know where to put this. So number 1 is linear and proportional. All right, number 2, the y's go up by 10. I'm sorry, the x's go up by 10. We did this one yesterday or earlier. So this is the constant rate of change is 1/2. So let's look to see if it is a proportional relationship. And let me show you something just in case maybe you don't see it. But you see this right here? See the 0, 0? Well, that's an ordered pair. That's what we would use to put in an ordered pair to plot points. That's point 0, 0. So this right here is the origin. Since it's the origin, then I know that this graph is going to go through the origin, which means it's a proportional relationship. But let's pretend like we didn't know. We got all the time in the world, right? So let's do 5 over 10. Let's do 10 over 20, 15 over 30, and 20 over 40, and 25 over 50. These all go down to 1/2. Very sloppy. So the constant ratio is also 1/2. So remember, for proportional relationships, we're looking between the numbers, or the relationship between each number inside the table or ordered pair. To find the linear relationship, we're looking at the change, or the outside, how the y's change compared to how the x's change. So this is linear and proportional. Just so happens that both of these have the same constant rate of change. Okay, let's look at this one. 12 goes to 24, 24. This goes, oh man. Okay, let's take a look at this last one. So all your y's are all your x's, are going up by ones. So 12 over 1, okay? Now let's do 24 over 2. And let's do 36 over 3. And let's do 60 over 4. Now, I've already determined that this is not linear, by the way. So I'm just showing you that it might be proportional, or might have a constant ratio, but it's still not going to be linear. Because this is 12, this is 12, this is 12, and that's 12. So this one has a constant ratio, but it does not have a proportional relationship because it has to be linear. So this is not. This is, and this is. Very sloppy. Now on this one, I just want you to look at the graph. So let's say this is 4 and this is 5. we can tell they're linear by the way the graphs are. Now, you can tell by looking that they're proportional. And how do you know just by looking at the graph if they're proportional? First, it has to be linear, and they both are. And they also have to be going through the origin, and they both are. So they need to be going through point 0, 0. So I know that these are linear and proportional. Okay, so I hope that you know a little bit more about constant ratios and proportional relationships, and really what to do with the data inside the tables, because you guys were on the right track, but you were using the data like you would if you were checking it for proportional relationships instead of linear relationships. This has been one woozy of a lesson, but I think the more you do it, the more it'll make sense. But peace out.